Good morning. So we are on to periodic dynamics, and so the primary reason we are doing periodic dynamics in this class is to really lay the foundation for chaotic dynamics. So there are a bunch of concepts that is extremely useful for chaotic dynamics, but it's actually a lot easier, a lot more intuitive to first grasp the concept in the context of periodic dynamics. I mean, these concepts like ergodicity and Lyapunov exponents, right, and covariant vectors, they are actually can be very well defined for all kinds of dynamics, including fixed points and the periodic dynamics. But they are just so trivial if you're looking at a fixed point that it doesn't really make sense to talk about them for a fixed point. But as soon as we get into periodic dynamics, it starts to make sense to talk about the ergodicity and Lyapunov exponents and the covariant vectors. So we are going to be introducing these concepts on this simpler context, right? Rather than doing them in chaotic systems, which might be actually confusing, right? We are going to see all the computational methods we use for these concepts is almost trivially generalizable to chaotic systems. But the result you're going to get is going to be different. Okay, so last lecture, we ended in introducing periodic dynamics for a map, right? It's the most simple periodic dynamics possible. It's a period 2 map in 1 dimension, right? So we started by basically taking a stable map that's like that, right? So if this is xn, this is xn plus 1. If we have a map that's shallower than 45 degrees, we can show that the Jacobian always have a magnitude of less than 1, right? So basically you can prove using the contraction theorem that there is a stable fixed point, and in this case at the origin. And as soon as we start to increase the slope of the map at the origin beyond a slope of 1, the fixed point becomes unstable. There is a bifurcation happening. We'll talk a little bit more about bifurcation later on. But the fixed point is still a fixed point, but now becomes unstable. The trajectories are going to, if you start a x0 around the origin, you're going to see x1, x2, etc. are going to be progressively further and further away from the origin until it settles down at the intersection of this red curve with the, if the red curve is symmetric, it will settle down at the intersection of the red curve with the 45-degree line. So these two are not. These two are fixed points, right? So this is actually the one fixed point becomes 2 fixed points. What we are actually discussing in lecture last week is actually the opposite case, where we have xn and xn plus 1, but the slope, instead of being positive, they are negative. So initially we have a fixed point still at the origin, right, except for the graph being flipped. And as we increase the slope, now it's the negative slope to over here. What happens is that, again, this fixed point becomes unstable, and instead of settling on either of these fixed points, it settles down on the intersection of the red curve with the negative 45-degree slope line, if the map is symmetric. But instead of being a fixed point over here, unlike in the left-hand side case, it is a period 2 dynamics. Because if x0 is at this point, then x1 is actually going to be at this point, and x2 is going to be back at this point. It's a back and forth. The sign of xi flips from negative to positive and backwards. Okay, yeah, you have a question?
But for this one that has a positive, it just sticks just positive or negative, right?
Yes, for the positive slope, it's actually not a periodic dynamics, right? It's actually the single fixed point bifurcates into two fixed points, two different branches. So depending on the initial condition, it will either go more and more positive or more and more negative towards the either fixed point.
So it's a fixed point, but there is a bifurcation on that point.
Exactly. Yes. Yes. It's the same type of bifurcation, but on the left hand side, it bifurcates into two fixed points. On the right hand side, it bifurcates into a periodic cycle.
But when we have a bifurcation, it's not going to be like a periodic one. When we have a bifurcation.
Can you say that again?
So because bifurcation means that there is a fixed point and there is a two branch, right?
Right.
So when we have these two branches, it's going to be like a limit cycle, right?
Well, it can either be two branches being two fixed points, or it can be the two points on the orbit of the living cycle. Right. So either way, it's called a bifurcation. Okay. All right. So this is the simplest periodic dynamics. Yes?
So why do we get two fixed points on the left column and periodic dynamics on the right column?
Yeah, that's because the on the left hand side the slope is positive, on the right hand side the slope is negative. Right, so once you have a negative slope, what happens is that if xn is positive, the next x is going to be negative, right? So if xn is positive, if you follow this map, xn plus 1 is going to be negative. So it's always a map between positive and negative, except for the black case when the slope is shallow, it oscillates while reducing the magnitude. But for the red case, it oscillates while increasing the magnitude until it settles over this periodic cycle. On the left-hand side, if xn is positive, xn plus 1 is also positive, right? For the black case, it doesn't oscillate, it just slowly shrinks into the origin, while for the red case, it just increases in magnitude until it settles at either the positive or the negative fixed point. That's just how the map works. So this simplest periodic dynamics is actually exactly what happens if you look at the Poincare section of the van der Pol oscillator, right? The van der Pol oscillator is a prime example of a periodic cycle. So this is the okay. It's the second derivative of a state x, or is equal to minus x. So if you just have the second derivative equal to minus x, it's going to be a harmonic oscillator, right? Just like a mass spring system. The acceleration is equal to the negative of the position, right? That's exactly a spring or a electric oscillator. Actually, the van der Pol oscillator is first derived modeling an electrical circuit, right? That's that actually generates periodic and non-sinusoidal signals. So if you just have this, it's a sinusoidal signal generator with arbitrary amplitude. But if you add some nonlinearity, if you add a mu times a minus x squared times x dot. Actually, I think here is usually an see. Okay, yeah, that's right. So this is the formula of the van der Pol oscillator, and usually we write it into a two-dimensional system by setting y equal to x dot, right? This way, we convert the one-dimensional second-order ODE into a two-dimensional first-order ODE. So basically, we get dx dt is just equal to y, and dy dt is equal to minus x plus mu times a minus x squared times y. So y is x dot, right? So this is usually how we code up the van der Pol oscillator using tools like ODE-int. So let's try this and look at how the van der Pol oscillator behaves. So again, we are going to denote the collection of x and y as u, right, as our state. And so du dt for van der Pol oscillator with a u and t would be, let's first set x and y is equal to u dot reshape 2 and minus 1. So basically, we are going to split the first half of u to be x, the second half of u to be y. We're going to be returning just a combination of dx dt and dy dt, right? So let's that which is du dt, okay? And let's compute what is dx dt. So according to our formula, our dx dt is just equal to y, and dy dt is equal to minus x plus mu times a minus x square times y. And we have to define mu and a, so let's just make them to be 1 for now. All right, so with that, just from PyLab import all, and from scipy.ode integrate import ODE-int. All right, so let's actually define a set of initial conditions. So let's actually make n initial conditions, say 100, and set our x to be all zeros and y to be a random collection of n states. And let's make them symmetric and with a magnitude of 3, right? So the maximum and the minimum are going to be -3 and 3. Yep. Random dot. Okay, so let's see. Zeros. Thanks. And let's say ODE-int du dt, and let's ravel u0, and let's set t equal to length space of 0. Let's integrate for 10 time units with a time step of 0.01. All right, let's make sure that works first. Oh, by the way, if you submit your homework as a Google Colab document, please share the link. Share the document with my Gmail. So chichi.wang@gmail.com. All right, thanks. Okay, so looks like it's working, and let's actually just plot. Okay, let's actually make u is equal to u dot reshape. So the first dimension is the length of time units, and 2 and n should be the dimension of the solution, right? 2 by n. So let's first plot u, the first dimension, which is x. The second dimension is going to be y. Okay, let's just so I don't want to see the output. All right, so this is what the solution of the van der Pol oscillator looks like. So our starting point are a random set of positions on the y-axis, because we set x to be a bunch of zeros, right? And we see that if we start with a positive y, the trajectory moves towards the right, right? Because dx dt yeah, dx dt is equal to y, right? So basically, our dx dt, our x would move towards the right hand side when we start with a greater than 0, with the positive y. And if we start with a negative y, the trajectory moves towards the left. But it doesn't move back to the same magnitude. And we can actually examine this a little bit more by making it a little bit bigger. So let's take a look. Let's first start from the origin and see that it's actually clearly a unstable fixed point. If we look at the gray trajectory, right? We started at a slightly positive y. It loops around and comes back at a negative y, but with a larger magnitude away from 0. Okay. If we start a slightly negative y, it loops around to a positive y, but also a larger magnitude than the starting one, right? But it seems that there is as you start from a larger and larger magnitude in y, there is some point, like roughly over here, that if you start with a negative y, you loop around and come back to a positive y with the same magnitude. And as you go even further in magnitude in y, you actually have a trajectory that loops around and end up at a smaller magnitude. So if you think carefully what that means on the Poincare section, right? So the Poincare section here is actually, it's my choice of the Poincare section, right? It's just the y-axis. And the Poincare map for this dynamical system is defined as the first return map, right, of the trajectory. That means if you start with the initial condition on the Poincare section, where does the trajectory first return back to that Poincare section? The map between one point and another point. Because the Poincare section is one-dimensional, right? That gives me a map from a one-dimensional manifold, in this case just a one axis, back to the same one-dimensional manifold. Right? Does it make sense what the Poincare map is in this case?
So all of them doesn't matter when we start goes to 1, right? End up at 1.
So I think what you mean is that no matter where you start,
yeah,
if you loop for long enough time, you end up at the same location, either here or here on the Poincare section, right? Yeah, that is actually correct. Because if you think about carefully what these trajectories mean, if you draw the map between, let me call it yn, right? That's the y of your initial condition, and yn plus 1, that is where you hit the Poincare section the next time on the trajectory, right? So we have been doing the simulation of if you start with the y0, right? What is y1? But if you keep integrating over the trajectory, you go from y1, which is also on the Poincare section, to y2, right? Which is on the other side, also on the same Poincare section. And you can keep going. So this map is obviously have a fixed point in the origin, right? That's right at the center, but it's an unstable fixed point. If you start from a slightly positive y, you end up at a negative y with a much larger magnitude. If you start with a negative y, you end up with a positive y with a much larger magnitude, right? So there is a very high negative slope at the origin. But at some point around y equal to 2, the trajectory starts to map back to itself. So 2 and -2. You start to get a point like that, which means the curve has to curve back, right? And also you have -2 and 2 here. So if you follow the Poincare map, the map is something like this, which is exactly what we are drawing previously, right, for the simplest periodic dynamics. So this is really an example of using the first return map on the Poincare section to simplify certain aspects of the Van der Pol oscillator into the simplest possible periodic dynamics. Yes?
Sorry, what do yn and yn plus 1 mean in this context?
Oh yeah, yn and yn plus 1 means the nth time a trajectory hits this Poincare section, x equal to 0. And yn, that's the location of the y when the trajectory hits that section, right? And yn plus 1 is the y at the n plus 1th time the trajectory hits that Poincare section. Yeah, so let me just the y location when the trajectory starting at x equal to 0 and y equal to y0, right, hits the Poincare section x equal to 0 for the nth time. All right. Yeah, in the future, we'll look at other similar Poincare maps by drawing different Poincare sections. In general, a Poincare section can be any manifold, right, on the phase space. But computationally, it is almost always easier to think about a Poincare section that's that has a constant value in one of the axes, right, or a constant value in some transformation of the coordinates in the phase space. Yeah. Does the Poincare section have to contain the fixed point or not? No. Yeah, and no in general, but actually in a lot of the cases, we'll find it actually very illuminating when we draw a Poincare section that cuts across a fixed point. So later on, we'll also look at Poincare section for the Lorentz system, and it turns out it's very illuminating when we actually cut through the two fixed points of the Lorentz equation. Okay, so now armed with this understanding of basically we can understand a periodic dynamics in continuous time by drawing a Poincare section and convert it into a periodic map. We are going to start thinking about a few concepts in dynamical systems, and we'll first think about what these concepts mean for a discrete time periodic dynamics, just like the map we are seeing over here. Okay, and then we'll generalize to a continuous time periodic dynamics. So the first thing is, what is ergodicity? So let me just get a bit of concept. How many of you have learned about the ergodicity before? Okay, so I see a lot of you raised the hand. What does ergodicity mean? Like,
it means that if we have some solution, be average in time. So no matter when from where we start as initial condition, we choose the initial condition, both of the time average will be same.
Okay, so here we get one definition. So definition one, right? So that's basically when we averaging in time, it doesn't matter where we start, right? So
Regardless of initial condition,
yeah,
we'll get the same answer, time average.
in time, it does not matter where we start. So mathematically, what that means? It means if you have a trajectory, right, u as a function of t, let me actually represent it in discrete time dynamics. Okay, if I start with u0 and map it to u1, so u1 equal to f of u0, u2 equal to f of u1, etc. Then what does averaging time doesn't depend on initial condition mean? What is the rigorous definition of an averaging in time?
If you have an observation, choose observation,
Uh-huh.
time average that.
If you choose an observation, and what does an observation mean in this case?
Or here,
Hmm?
Integrate. So
A what?
integrate
Integrate over what?
over time, over your points, I guess, if we're discrete.
Sure. In this case, our time is discrete, right? So integration in discrete sense means just the adding, right? So basically, we're adding, but adding what?
it could be anything, objective function.
It could be any objective function, right? So the so-called observation is a function, right? So let's say j is a function of u. So we are adding j of ui, where I goes from, let's say, 0 to n. So this is a integral or addition, right? But when we are saying averaging time, what does average mean? Average means we have to divide the sum by how many we are adding, right? 1 over n. So that's a time average. In a continuous sense, we're just going to be replacing the summation with an integral and this big N with a big T, right? Okay, so the average doesn't depend on initial condition, which is u0, right? But how long do we have to average in order for the average to not depend on the initial condition?
It's very long.
Very long. How long is very long? Sorry? N goes to infinity, right? It's really the limit of this quantity as n goes to infinity. Does not, right? So let me say, let me actually call this j bar. J bar as a function of u0 is defined as this limit, right? Or another way to say it is limit of n goes to infinity. Let's write it as an explicit function of u0. I goes from 0 to n, j times f to the ith power of u0, right? So f to the ith power is basically f compound with itself for I times, right? F of 0 is the identity map. F of 1 is just f. F of 2 is f of u, right? Etc. So this is really the definition of the infinite time average function, right? Obviously, if you write it like this, the only thing this j bar can depend on is what? It's u0, right? The only thing that appears over here, of course, is j, and Yeah, U0 is the only dependence like J bar can depend on. Okay, so by saying that the average does not depend on initial condition, what we are really saying is that this J bar is a constant function. Okay, so basically J bar is a constant function. All right, so this is one definition of ergodicity. Is that the same ergodicity that everybody learned?
It's like another one that I kind of learned.
Okay, please go ahead.
Is the solution, or like the solution kind of covers all the solution space, regardless of where you start from.
So the solution covers all the solution space, no matter where you start from. That's actually a very good way of saying it intuitively. Did anybody learn the same concept of ergodicity before? And I want to help to really say what you have said in a more mathematical way. All right.
I didn't get the point.
So no matter where you start, no matter where your initial condition is, if you have like a domain where your solution can be, it covers all of that. Like the solution, like the trajectory of your solution, that covers all of that entire space.
Okay, so that's actually another definition, and it's a more measure theoretic definition. All right, so when you say a solution space, right, what that refers to? That actually refers to obviously not the entire phase space, right? For example, you've probably seen like a chaotic attractor, like in the phase space, like the Lorentz equation, right? It kind of comes up as a butterfly type of shape, right? And by the solution space, that butterfly shape is actually what you mean, right? And that obviously is not the entire phase space. The entire phase space extends to infinity, for example, for the Lorentz equation. So what does it mean by the solution space? How we usually define what you call the solution space, where your trajectory actually visits, is through a probability measure. Okay, how many of you have studied the measure theory probability before? Measure theoretic probability? No? Okay, so let me maybe introduce a little bit more measure theoretic probability over here then. So in order to define a probability for something like a phase space, we first of all need a collection of sets, right? So because what you call the solution space is actually a subset of the entire phase space. So what is a probability? A probability measure we usually call a rho is a map. It's like a function, but it's actually a even higher dimensional function than a typical like multivariate function we are thinking about. It's a function that doesn't map from a number to a number. It doesn't even map from a vector to a number. It maps from a set to a number. Okay, so it's from a set to a number. And for probability, for it to be called a probability measure, the number has to be between 0 and 1, right? I mean, a general measure can map from a set to a number between 0 and infinity, but for it to qualify as a probability measure, it has to map from a set to a number between 0 and 1 to qualify as probability. Okay, so as you can think about, if you define a probability in the space between 0 and 1, right? A uniform probability between 0 and 1, for example, it's a map between any set. You can actually not any set. There are. I'm not going to go through all the sigma algebra and stuff that you typically learn like in a measure theory class, but you have a very wide range of sets you can define, right? Usually in a Rn space, and it's actually the set of sets you can draw a probability measure on is usually so wide that it actually takes a lot of effort to construct a set not being measurable. So let's just ignore the part of sets that are not measurable for now. And it maps, for example, the uniform probability maps a set within 0 and 1 to really how long that set is. Right? So if the set is a contiguous range of numbers, then it maps from that set to the number that represents the length of that contiguous set of numbers. Okay, so that's an example of a probability measure. But for any probability measure, as long as it maps a set to a number and satisfies a certain conditions. For example, condition 1 is row of an empty set has to be what? 0, right? I mean, if you look at the probability of nothing, right, it has to be 0. And the probability of the entire thing, right? So no matter where you're defining the probability measure on, for example, you are defining on the phase space of a dynamical system, the probability measure of the entire phase space has to be equal to 1, right? So basically, the probability of something impossible has to be 0. The probability of any possible outcome has to be 1, right? So that's usually how we think about it. It also has to define the so-called countable additivity. So basically, if you have a series of disjoint sets, so if you have A1, A2, etc., just a pairwise disjoint, then row of A1 plus row of A2 plus ... has to be a convergent infinite series, right? Has to converge as just a plus row of an as n goes to infinity, has to be equal to the row, the probability of the union I goes from 1 to infinity of ai. Okay, so this is actually a lot easier to understand in the finite sense if there are finite many n's, in the sense that starting from an plus 1, they're empty sets, right? So that you can ignore the row. I mean, the row of empty sets are all 0. So this actually generalized to a finite, specializes into a finite set of numbers of sets. But for a finite number of sets, again, you can take the uniform probability measure between 0 and 1 as an example. So take an example. Okay, so if row is uniform probability in the set 0, 1, okay, and a row of any a, b, so let's make it the one-sided, is equal to, it maps from a set to a number that's equal to b minus a if b is greater than a, greater or equal, right? Because if they are equal, it's an empty set and you get the 0, right? Okay, And as an example of this convergence, row of 0 to half plus row of half to 3/4 plus row of 3/4 to 7/8, right? Plus etc. plus row of 1 minus 2 to the n, 1 over 2 to the n to 1 minus 2 to the n plus 1, right? So basically, I'm adding a series of progressively smaller numbers that has to be equal to, as n goes to infinity, right? That has to be equal to row of the union of all these disjoint sets, which is going to be 0, 1, right? And basically that has to be equal to 1. And if you look at this series of numbers, this is basically saying that half plus quarter plus 1/8 plus etc. has to be equal to 1. I mean, that's just an example of what has to be satisfied by a probability measure. Okay, and so in a dynamical system, we are actually using such a probability measure to define the so-called all possible, like all the solution space. And let me just give you a few examples. Let's start from a trivial example. Okay, a trivial example is okay, so let's say f of x, f of u is equal to, well, half of u. Okay, so can somebody tell me what does that dynamics converging to, right? What is the so-called all the solution space that you are going to go to? You are going to go to no matter where you start. Yeah, it goes to 0, right? So how do we define a probability measure that quantifies, I think, what you just said, right? And no matter where you start, you end up exploring all the solution space. In this case, what is row of a set A? It's 0?
Starts with u0. I mean, initial condition for u.
Well, so row so remember, like what condition row has to satisfy, right? Just these two. Row of empty set has to be 0, but row of the entire phase space has to be equal to 1. So how can you define a probability measure that helps quantify what the solution does eventually, no matter where you start? Well, the solution here, no matter where you start, you eventually just come to a single point, right? So how can we define a probability measure that quantifies that that tells you that the solution space is just the solution you end up to is just a single point? Well, you can set it to be equal to 0 no matter what A is, right? But then it would not satisfy the second condition. It would be a measure, but not going to be a probability measure.
Equals to 1 closer you get to 0.
Can you say again?
Equals, so the sum of all of it equals to 1 as you get closer to 0, I guess.
Sum of that equal to So row of a set, right? You have to give a number depending on what set I give to you.
So distance from 0.
Just the what? Distance from 0?
Yeah.
So how do you define the distance from a set to 0, right? Like radius of a, right? That would be smaller if you're close to 0, right? But what I want is a number from 0 to 1. Well, let me tell you in this case. This number is going to be either 0 or 1, depending on just the one feature of the set A. What feature is that going to be?
At 0 or not.
Yes, if you include a 0 or not. All right, so the measure of the set A is going to be 0 if the 0 point is not containing A, and it's going to be 1 if the 0 point is in A. That's a perfectly fine probability measure, right? The empty set doesn't contain 0, so it's going to be 0. That's the first condition we have to satisfy. The entire phase space contains 0, and the probability measure of the entire phase space is equal to 1. That's also satisfied. It also almost easily satisfies this additivity condition, right? Because all of these are disjoint. So either none of them contain 0, in which case the summation of a bunch of zeros is equal to 0, or only one of them contains 0, right? So the summation of one and a bunch of zeros is equal to 1. So either way, I'm good. So this is an example of a discrete measure that actually, the discrete measure means the measure is concentrated, in this case, a single point. All right. Okay. A second example is actually going to be a periodic dynamics. So, example 2. And the f of u is going to be exactly what we just draw. So something like this. So it has two symmetric points that intersects with the 45-degree line. It's the first return map of the van der Pol oscillator on the Poincare section of x equal to 0. Okay, so in this case, can you help me define what the long-term solution is going to end up doing? Well, we know intuitively that it just oscillates between these 2 points, right? How can you use a probability measure to define that?
I think that the idea of first example, so we say when there is no 0
Mm-hmm.
or solution space, then the probability is 0, right?
Yep.
But whatever we put, it's going to be 0.
So you didn't get the first example, right? So imagine the first example is a map just like that, right? So imagine you can define a set, right? So if A is equal to, let's say, from 1 to 2, right? Then row of A is going to be what? According to this, it's going to be 0, right? If A is going to be equal to, let's say, -1 and 1, row of A would be 1, right? So basically, it's a map between a set and a number, and the only thing that distinguishes different sets is that the only thing that row cares is whether the set actually includes the origin or not. All right. So now can somebody help me generalize this probability measure that defines the set of solutions that we ultimately converge to on the second example?
So you probably measure just 0, 1 if fixed point is in the set.
Well, that's good, but the map actually doesn't have any fixed points, right? It has 2 points, both included in the same limit cycle, in the same periodic limit cycle.
So the absolute value of your limit cycle value.
So sorry?
Radius.
The radius of the
Maybe like some. Yeah, I mean, if it's like a cycle or something, it's like a ring around it. Of like if the set includes that ring, then I'm not even.
yeah. So in the first example, right, we use the basically a probability measure to. Okay, so let me say like why in the first example. First of all, this probability measure works. Okay, so it satisfies a certain set of properties. So first of all, is that rho is preserved. I'll see what this preserved mean on the map F. So what does that mean? That means rho of a set A is going to be equal to rho of f of A. So what is rho of f of A for any set A? So what is rho of f of A? F of A is where f of A is the collection of f of x for any x in A. So basically, if we have a set, right, the map actually maps the set to another set. That other set is f of A. And by saying that this is preserved on the F is that no matter what set you have, after you map it using the map to a different set, right, that different set, although being different, has the same probability measure on the rho. So why is this true for the first example? This is true because if you define a set, for example, you define a set over here. Let's say I have A over here. Okay, after you map it, f of A becomes this. So this would be f of A. In this example, both A and f of A has a measure of 0, right? So that works. If you define an A that does include the origin, if A is this, then f of A is the corresponding area in the y-axis. It would also include the origin, right? So in this case, both rho of A and rho of f of A are equal to 1. So this is what the definition of a rho is preserved on the F mean. Or in other words, there is also what's saying like F is a measure preserving map, right? Where the measure is defined by rho. Okay, so this is also another way to say it. F is a measure preserving map.
I think we have limit cycle points. If the range is out of that point,
Yeah.
it's going to be 0. But if it's
Yes, that's a very good point. So for the second example, we can use exactly the same, we can define exactly the same value of rho if A does not include either fixed point, right? So that's an excellent point. So basically, let's just do our second example. Yeah, so I'll let you complete your answer right away. So if let's say this is x plus, this is x minus, right? If x minus, if neither x minus nor x plus is in A, okay? Yeah. How about other sets that include maybe x plus or x minus?
the other one should have both of them from minus from x minus to x.
So you're saying the other case is if x minus is in A and x plus is in A, what?
The range, I mean, because when it goes to x plus, then it goes to x minus again, so it's vice versa.
Okay.
So we cannot say just half of the range, just the positive range, because it needs to go to the negative one. So in that case, it's going to be 1.
So you're saying like if both x minus and x plus is included in the map, it should be 1? The measure of that should be 1?
I mean the range. I'm thinking about the range, not exactly those points.
The range, you mean the
Bracket x minus to x plus. The range. Bound.
okay, so sorry, can you say again?
Would be the solution for the FU intersecting the point line.
Right, we are saying like the intersection of the f of u with the 45-degree line are at x plus and x minus, right? These are the intersections. Okay.
It's not 1.
It is equal to 1. All right. So this is the case where, for example, like the entire phase space actually includes both x minus and x plus, right? So basically, we can, let's say we have 4 cases. We have the first case and the last case already defined. So the first case is if neither points are within the set. The last case is if both points are within the set. And because the first case actually includes the empty set, so the value has to be 0. The last case includes the entire phase space, so the value has to be 1, right? That's basically by these two are checked. Okay, now we still have 2 cases remaining. That's what if one of the x's is within the set but the other is not? What should the probability measure be? 1/2. And actually that's correct, and that's the only answer possible. Why is that the only answer possible? Well, the additivity by itself, that's right, but it doesn't actually guarantee the value has to be half. For example, if I only need to satisfy the additivity, right, then any sets that include x minus but not x plus can have a measure of 0.1. But any set that include x plus but not x minus can have a probability measure of 0.9. That also satisfies the additivity, right? In this case, the argument is actually this measure preserving property. Okay, so if you map a set that include x minus but not x plus, then f of a. So if so let's say if a contains x minus, then f of a would contain x plus, right? And if a doesn't contain x plus, then a also and then f of a does not contain x minus. Oh, f of a, sorry. Okay, so if a has a whatever probability that a has, whatever row a has, f of a also have to have the same probability measure, have the same row. And we can easily make a and f of a disjoint, right? For example, a can be the set that only includes x minus. And as a result, f of a would be the set that only includes x plus. Then row of a plus row of f of a has to be equal to row of a union with f of a, right? So, and the union of them contains both x plus and x minus, so that has to be equal to 1. And that means both has to be equal and they add up to 1, which means the only possibility is half. If I would just say otherwise. If one of them included, then the other did not. All right. Okay. Yeah. So we can do this, and we can also if this is the only periodic cycle, we can also show that the none other probability measure simultaneously satisfies all the requirements for rho to qualify as a probability measure and the measure preserving property. Okay, this is actually the uniqueness of such measure is another definition of ergodicity. So an ergodic map F has a unique row that satisfies the measure preserving property. Okay. So now we have defined this row, this probability measure on two cases. One is a fixed point, another is a periodic cycle in discrete space. Let's actually consider a case where this type of ergodicity is not satisfied. Okay, so in both cases, in both the trivial fixed point and the simplest periodic dynamics, we can see that both concepts of ergodicities are satisfied. The first concept is the long time averaging converge to the same answer no matter where you start, right? For a fixed point, as you keep iterating, right, for a global stable fixed point, no matter where you start, okay, you end up at the same fixed point. So as you average over longer and longer time, you have a longer and longer proportion of your trajectory closer and closer to the fixed point. All right. So basically, you can prove that your J average is going to always converge to the same answer, which is just the J evaluated at the fixed point, right? As long as J is continuous. So for fixed point, it's pretty easy to say that. And a fixed point also has a unique probability measure that is preserved on the map. And for the periodic cycle, you can show the same. Again, as you're averaging over a longer and longer trajectory, the trajectory is going to be closer and closer to the pair of points, right? That lies on your periodic orbit, and the percentage of time the trajectory spent on either point is exactly half, right? Because the trajectory just oscillates between these 2 points. So the J bar actually is going to converge to the average, the arithmetic average of J at one point and the J at the other point. Okay, and you can generalize this to, for example, trajectories with a period 3 cycle, period 4 cycle, etc. The J bar will just converge to the average between the J evaluated at these X number of points, no matter what X is, right? And you can also show that these type of unique probability measures is also true for any period, right? So except for if you have a period 3, then the row of any set that contains only one of these numbers would be 1 over 3, right, instead of 1 over 2. Now, what kind of systems does not have ergodicity? It turns out that the very first thing we looked at today, this one, right, actually violates ergodicity for both senses. Why? So for the first sense, right, when you're averaging over a long time, does the long time average depend on the initial condition? Well, yeah.
The problem.
Yeah.
If we start with some initial condition, it goes in one direction.
Yes.
But if we start with another one, if there's a bifurcation, it goes another one. So
exactly.
we don't have the same.
We don't have the same thing, right? So if we start with the positive x0, the solution converges to the positive answer. And if my j, for example, my jx is equal to x, then the long time average of j would be positive. If I started with a negative x0, then I get stuck at the negative solution. My long time average of j will be negative. So basically, in this case, so let me say, when I have a map that is a counter example of ergodicity. Okay, so I have a map that's like that. I have 2 fixed points. Okay, so again, I just call it x plus and x minus. And if my jx is equal to x, then what is my j bar of x? My j bar of x is going to be either 1 or, well, my j bar of 1 is going to be either x plus or x minus, depending on if my x is greater than 0 or x is less than 0, right? If it's 0, it's going to be equal to 0, right? Okay, so basically j bar of x is not going to be independent of the initial condition. And how about the probability measure sense of ergodicity? Can you construct examples of rows, examples of probability measures that satisfies all the conditions required for probability measure, and the condition required for the measure preserving property, that rho of A is equal to rho of f of A. Can you show that this system is not ergodic in the sense that there are multiple rows that satisfy all the properties simultaneously?
I guess you could say it's rho equals n if you start with a positive number, and when it's 1 minus n, if you start with a negative number, so n can be whatever, you still add.
Yes,
So
that's an excellent counterexample, right? So I can define rho to be similar. So I would be 0. I still define rho to be 0 or 1 if neither or both are included in the set A. So if neither x minus nor x plus is in A, and 1 if both x minus and x plus are in A. But in the middle, when one of them are in, the other is not in, I have flexibility of choosing, right? Well, I still have to satisfy the constraint that rho of A plus, I still have to satisfy the constraint that if I have two sets, right, one set include x minus, not x plus, the other set include x plus but not x minus, the union of these two sets have to have a measure of 1, right? So the sum of these rows on these two sets has to add up to 1. But I now have complete freedom of defining which this is. For example, I can define as m, that's what you said, right? If x minus is in A but not x plus, I can define it as 1 minus m if x plus is in A but not x minus. So why would this probability measure when m is not equal to half would work for this case but not for the purple case? This analysis actually gives you really the intuition of ergodicity. It's because for this map, if I have A that includes x minus but not x plus, right? A that includes this point, the map actually would still only include that point, right? It maps a positive branch to a positive branch. But if you look at the purple case, if you have a similar set A that includes the positive branch, f of A would be include x minus, would go to the negative branch. So it goes in between them, right? While in this case, because if I started near x plus, I'm stuck with x plus. I would never visit x minus. Okay, so basically, when you have an ergodic system, an ergodic map, starting from anywhere, you actually get mixed around. You actually visit other places. Okay, and so that usually gives you both the measure preserving, the uniqueness of the measure preserving. Uniqueness of the measure that has the measure that the map has the measure preserving property, and also gives you that the long time average is independent. Well, let me qualify this independent. Is almost anywhere independent of the initial condition. Okay, so here you see this special condition of if x is equal to 0, j bar is equal to 0. That's also true for this case, right? If you start with x exactly equal to 0, you would not get that uniform j bar, right? So for the purple case, for the purple case, we have this map. My j bar of x is equal to what? It's either equal to half of x plus x minus, or 0, right? If x is equal to 0, x not equal to 0. So j bar is not exactly a constant, but it is almost everywhere a constant. By almost everywhere constant, what do I mean? So have anybody seen the word almost everywhere? So what does that mean? Yeah, so it is true. A statement is a true almost everywhere, means it is true for all the points except for a measure 0 set of points. And this measure 0 is not that probability measure. It is the regular, what we call the Lebesgue measure, basically the measure that actually measures the width of the set, right? In this case, like there is only one point for which the statement of constant j bar is not true. So it is constant almost everywhere. So let me just go back to my definition 1. Is a constant function almost everywhere. And we also have to say for continuous function j. All right. So that's our 2 definition of ergodicity for discrete maps. So before the end of the lecture, let's just go really quickly and generalize the concept of ergodicity to continuous dynamical systems. Just okay. So for continuous dynamical systems, the 2 concepts of ergodicity are very similar. So definition 1. If we have a differential equation, du dt equal to f of u, we use the phi with a superscript t, right? u0 to denote the solution ut starting with u0 equal to that initial condition. So basically, we are really using a map to denote a continuous time dynamical system, right? Except for this map is parameterized by a continuous time variable t. Note the similarity of this notation with our f to the kth power, right, in the previous notation. So f to the kth power is basically taking u0. So this is analogous to f to the kth power of u0 being mapping k times starting from u0. Okay, so this phi of t is our notation. Then, like our j bar as a function of u0, which is defined as the limit of t goes to infinity, 1 over t. So that's the long time average, right? 1 over t times the integral over a length of t is the time average. And we are time averaging an observable j that's evaluated at the solution at time t, starting with u0, right? So this is using our notation. And again, from this notation, we can see that the only thing that j bar can depend on is u0, okay? Is a constant function almost everywhere. Okay, so this is again for any continuous j. All right, so that's our first definition. So that the second definition is also very similar, right? So the second definition is there is a unique probability measure rho such that there's a unique probability measure rho such that the rho is preserved under the map. So that means rho of A is equal to rho of the phi operated on A with any time. All right. Okay. So starting from the next lecture, we'll look at the concepts of ergodicity using the example of the Van der Waals oscillator, like for continuous time ergodicity. And then we'll also introduce another key concept, that's the Lyapunov exponent, all right, using the periodic dynamics. So I will see you on Wednesday.